Hello, welcome to our SRC annual review presentation in 2022. I'm going to talk about our task memory system design for AI ML accelerators and ML AI techniques for memory system design. We're trying to solve the data movement problem that's associated with ML AI and in general workloads. And clearly many workloads are bottlenecked by data movement today. And data movement causes significant performance energy problems. And this is true for the mobile end as well as the data center end. And we've been tackling a lot of issues related to machine learning as well as genomics in this particular task. And both in machine learning and genomics, you have very strong data generators. And the question is, how do we cope with these data generators that create these performance energy bottlenecks? Essentially, data is overwhelming our modern machines today. It's all kinds of capabilities, as we have done a lot of analysis in the past that we have presented in prior reviews. And it's causing a lot of energy problems. And as we have shown in our prior analyses of multiple different types of workloads, a significant fraction, essentially most of the total system energy is spent on data movement today. Basically, we want to design intelligent architectures that handle data well. We don't want architectures where data overwhelms the components. We also want to take advantage of the flowing data so that we can make better decisions using machine learning, for example, in our controllers. And we want to understand, exploit properties of data. Basically, we want to move from a processor-centric paradigm to a more data-centric, memory-centric paradigm. We want to move from a paradigm where controllers are making designer-dictated decisions to more data-driven, machine learning-driven decisions. And we want to move from a component-based myopic decision-making to a more data characteristic-aware decision-making. And we've discussed this in the past, in past annual reviews, this vision, and we've written papers about it, so I'm not going to delve into it. Let me jump into the overview of our task. Basically, in this task, we're specifically focused on designing memory systems to handle data well. And we're looking at the interplay between machine learning, AI, and memory system design. We would like to design memory systems for AI and machine learning workloads and accelerators. And we also would like to design machine learning techniques to improve memory system designs to make better decisions in the memory system. So we're looking at this duo, if you will. And these are the two major goals from our task description. We want to have an in-depth exploration of the memory system design for emerging machine learning accelerators, both for cloud and edge systems. And we're looking at both the on-chip and off-chip memory systems. And we also want to design practical machine learning techniques to improve memory system designs. And we're comprehensively looking at across the memory system for this purpose. I will not go through a lot of these slides that are already available on the website. You can find the primary results, task description, task deliverables, etc. I will give you a little bit more information about the task. These are the students involved in the task. We have a large group and we support them with additional support, of course, with cost sharing, etc. And we have a number of senior researchers also, which we're lucky to have in this task. Let me talk about some recent things that have happened. Minesh Patel, a student in our group, is a recent PhD graduate. He did a lot of great work, and his dissertation won the William Carter PhD Dissertation Award in Dependability, and he has multiple Best Paper awards. He's looking for research positions in case people are interested in looking for good people. We have 3 postdoc alumni. They already are lined up for different places or have started in different places. One of them is starting in academia, for example, in South Korea as an assistant professor. Gagan is joining AMD Research. And we have one more PhD student, Hassan, who is graduating soon, essentially. Gagan also did an internship at AMD Research this year. I will mention our upcoming TechCom presentation, which I will briefly talk about. Also, Juan is giving a TechCom presentation on our analysis of the UpMem hardware, including general purpose workloads as well as machine learning workloads. And I would recommend you take a look at it. If you want to look at an earlier version of this talk, it's already linked from here. We are lucky to have a lot of industry liaisons who have been providing useful feedback to us, and we look forward to future feedback, and we're open to other collaborators' feedback, internships, and visits. And this year, we had quite a few interactions with our liaisons as well as SRC companies. With Intel, we have a bunch of collaborative papers as part of this task. I'm not going to go through all of these in detail because we don't have enough time. And we have a collaborative paper with IBM. We have a project that has just started, a European Union project with IBM that's synergistic with this task. Essentially, it's called BioPIM. It leverages the emerging processing and memory technologies to enable powerful edge computing. I'll let you read the slides. These slides are available for people to look after, during, or at any time. But I will not cover everything on these slides. And in fact, there are a bunch of slides that I'm not going to cover at all. We had in-person visits and talks and discussions with a number of folks who are our liaisons, as you can see. And we had a keynote talk at the Intel Interconnect and Connectivity Summit. We have a bunch of posters in addition to these talks that we have in the annual review. There are 5 of them that are available. Please take a look at them. we'd be happy to get feedback on all of these. And some of these are actually to appear papers. We've been organizing some special sessions that are very synergistic with this SRT task. For example, we had a special session at ISVLSI where we featured 9 cutting-edge talks on in-memory processing, and we have the entire session on our YouTube channel. If you're interested, please take a look. And we've been open sourcing a lot of courses that are very synergistic and related, and these are also live streamed, so people in the world can join. Anybody who's interested can join and provide feedback. As you can see, there's computer architecture, there's digital design courses, there's a processing in memory course, genomics course, heterogeneous systems, hardware, software, co-design, and SSD course over here. Now, let me jump into what we're doing in this task and some recent results. Essentially, we have 2 thrusts: memory system design for AI/ML and AI/ML for memory system design. And we've been exploring a lot of ideas. I will go into some of them, but we will not have time to cover everything. But the slides can help you navigate. And we also uploaded all of these papers that I'm going to mention and I'm going to have on the slides. Basically, in the second part of the thrust, the key question we're asking is, can we somehow design fundamentally intelligent architecture that can learn from experience and make data-driven decisions as opposed to human-dictated decisions? We want controllers all over the place that can employ automatic data-driven policy learning, and they're all intelligent data-driven agents so that the memory system becomes much stronger and much more intelligent. The question is, how do we start? I'm going to give you some examples. Actually, not me, but I'm going to talk about the thrust 1, especially in my portion of this talk. And then Gagam will talk about a reinforcement learning-based storage management policy. And then Rahul will talk about a perceptron-driven off-chip load identification policy that both improve performance significantly. But let me give you an overview of what we have done this year. So these are results from 2020, 21. And in 2022, actually, we were even more productive because now we're exploiting what we have analyzed in the past 2 years. These are some works that we have published on real processing in memory systems and their analyses. And I'm going to focus on this one a little bit. And these are some works that we have published also on designing machine learning and genomics accelerators for various workloads and some processing in memory systems as well. And these are more of the thrust 2 works, as you can see. How do we use machine learning, reinforcement learning, perceptrons, etc., to improve memory system decisions? And there's a bunch of other works that I won't have time to cover, but you can find them online. Let me jump into some examples. So we've been doing a lot of analysis of processing in memory systems in the real world, specifically the UpMem system, which was the first system that was introduced as a general purpose processing in memory engine. But as you can see, there are a bunch of other systems that were introduced recently in 2021, 2022. And this picture doesn't even include many experimental chips and startups. So UpMem is interesting to us because we are able to have access to it. And these are general purpose processors next to each bank. And these are real. We have access to them. We've been analyzing them, developing benchmarks and explaining them to the world, essentially. This is one of Juan's presentations. You can see that there's a general purpose processor attached to a bank. Now, this general purpose processor has some limitations. For example, it doesn't have a hardware multiply instruction, but our results show that even without a hardware multiply instruction, it has benefits on workloads that even have multiply sometimes. So this is very interesting, I think. And I'd recommend you take a look at our papers. But basically, we developed benchmarks and micro benchmarks, and we released them. We compared the system to state-of-the-art CPUs and GPUs. We basically provide a bunch of takeaways on what makes a workload PIM suitable. We provide programming recommendations to take advantage of these systems, and we provide suggestions and hints for hardware and architecture designs of future PIM systems. And as I said, there's a TechCom presentation that will go into it detail, but you can also find a bunch of presentations. So let me give you some example takeaways. This PIM architecture is fundamentally compute bound because there's not a lot of computation. You can do the frequencies very low. As a result, most suitable workloads are memory bound. Even then, there are some workloads that benefit a lot compared to existing CPUs and GPUs. And the most well-suited workloads are still they don't have a lot of arithmetic intensity, basically. And they don't have a lot of communication across different banks, if you will. And there are a bunch of other takeaways that I don't have time to go over, but you can read our short papers as well as long papers. You can take a look at our benchmarks. We'd be happy to get contributions and get feedback. And these are all open source, as you can see over here. Okay, let me jump into the next work. So we specifically wanted to analyze machine learning training on this processing in memory system. And these are some works in this direction. These are under review. Well, the longer version is under review at this point. But basically, we wanted to understand the training and how this architecture benefits training. what are the shortcomings of the architecture in terms of training. And we essentially developed a benchmark suite over here. We wanted to look at classical machine learning algorithms first, because deep learning clearly is not going to be easy to begin with in this architecture without the multiplication support. We looked at linear regression, logistic regression, decision trees, k-means clustering. We characterized them on this architecture. We implemented them so that they actually provide benefits as much as possible. And we basically have compared them to CPUs and GPUs. And we have a bunch of new observations and insights. How can you optimize things? Fixed point representations help, quantization helps, hybrid precision implementations help. We make use of lookup tables, for example, to implement complex activation functions where the PIM system doesn't have native support for them. And data placement and layout is clearly important. And scalability is actually very nice for these systems, because the benefits scale with PIM-enabled memory as PIM cores are attached to different memory banks. So there are a lot of results. I don't have time to go over them. You can find them in this video over here. But there are a bunch of slides over here that I've provided that I will not go into, that provide a lot of interesting information, in my opinion. And you can take a look at them at your convenience. And clearly, you can take a look at the papers. We'd be happy to get any feedback on this topic. We're improving this work right now to include other machine learning algorithms and essentially more optimizations. Okay, let me also talk about one other thing that we did here. We analyzed the sparse matrix vector multiplication on the UpMem architecture. Remember that the UpMem architecture doesn't have a native multiplier. Even then, sparse matrix vector multiplication can be optimized on this architecture to provide benefits. And this is a very interesting work, in my opinion. We provide the first software package, open source software package, SparseP, for real processing in memory systems. You can download it, play with it, etc. And we extensively characterize it. And we provide recommendations for future architectures, software designers, etc. And we have 25 SPMV kernels with different formats. We compare these different formats, compression formats, for example, data types, data partitioning techniques, synchronization approaches, etc. And we provide the first comprehensive analysis across 26 sparse matrices. And we have a bunch of recommendations that I don't have, again, time to go over, but we have videos on this topic, and a paper was published this year on this topic. Again, these slides give some more insight onto what we have done. But again, I don't have time to go over these takeaways, but you can look at them at your convenience. Let me quickly talk about another system that we developed. This is not the UpMem system, but we wanted to develop a FPGA-based processing, FPGA-based infrastructure such that we can evaluate the processing in DRAM mechanisms end-to-end across workloads and systems. So essentially, we have an FPGA board. This is also open source, as you can see. And we violate the timing parameters in the memory controller of this FPGA board so that we can implement row clone operations, row copy, row initialization operations, as well as bitwise AND and bitwise OR operations. So we have limited processing capability, but this works with real DRAM chips where we can actually do these violations of these timing parameters. And by doing so, we can end-to-end evaluate the benefits of, for example, doing a row copy operation in memory called from an application. And we have the entire software stack as well as the hardware stack to enable this. We call this PyDRAM, essentially. And basically, one can do system integration studies, end-to-end workload evaluations with this, using real unmodified DRAM chips, or DRAM chips that actually support this. We just need to change the memory controller, of course, to be able to do that. And you can, of course, this paper describes, for example, data allocation and data mapping strategies that are important. And we see significant speedups by doing row clone, for example, copying. And we see significant throughput improvements with true random generators using DRAM. And again, I don't have time to talk about it, but we have a bunch of talks online. This is one of them. And these slides talk about some of the components and how we actually made this work, which I believe is fascinating and hopefully useful for people who want to do work on processing in memory and using memory. And this is our GitHub, this is our paper, and there's a longer tutorial video that you can also find. Let me quickly talk about some work that we've been doing to accelerate genomics applications very quickly, and then I will conclude. You can take a look at all of the other works online, and then I will give it to Gagan to talk about Sibyl. So we've been looking at genomics. Specifically, more recently, we have been looking at accelerating graph-based genomics, because the requirements of this is very different from linear reference-based genomics. Now, this is a more difficult problem because graphs have a lot of nodes and you have a lot of irregular accesses, and you need to we designed the first specialized graph mapping accelerators for genomics. And I will not go into a lot of detail. You can find, again, the talks and the slides, but we see significant speedups compared to existing software as well as hardware accelerators. And Damla, who was part of this task for several years, has recently given a talk on this topic at ISCA. And this is the work that is collaborative with Intel. And again, you can find more slides over here that talk about the problem, the solution, the accelerator design, as well as its evaluation over here, as you can see. Now, finally, let me quickly talk about GenStore, which is essentially another genomics accelerator that we designed to do filtering inside the storage system. So a lot of genomics accelerators reduce the computation overhead of genomics by designing heuristics, accelerators, and filters. You can reduce the computation overhead of genomics, but data moment overhead remains because you need to move huge amounts of data from the storage system to the computation unit and back and forth potentially. We're not even talking about main memory. Main memory is still interesting, but storage is even larger data moment. So the idea we have in this work is to filter reads that do not require alignment inside the storage system, such that storage system sends only a very small fraction of the reads to the computation or acceleration. And there are multiple different types of reads that we filter that we don't have time to go over right now. But there are some challenges to this because workloads exhibit different behaviors. How do you take that into account? And there are limited hardware resources in the storage system as well. So after all, we have a design that reduces computation overhead as well as data movement overhead, and that provides significant speed ups and energy reduction compared to best prior accelerators as well as software. And I'd recommend you take a look at our S+ paper, and Nika has a talk, detailed talk that explains GenStore. As I said, this is where I will stop. We have a bunch of other works that I don't have time to go over. These slides are available. We'd be happy to get any feedback at any time, any ideas, feedback. We're very welcoming to that. Now I will pass it on to Gagan, who will talk about Sybil, which is a reinforcement learning-based data placement mechanism in hybrid storage systems. And then Rahul will briefly talk about the Hermes work that's going to appear at Micro 22, which is essentially a perceptron-based prediction mechanism that can predict off-chip loads early so that you can start their requests and reduce the latency of long latency loads. Thank you very much, and I'd be happy to take any questions after their presentations.